Okay, in the last video we have discussed for different eigenvalues how the phase portrait will look like, right? So now what we will do is instead of looking into the eigenvalues, we will directly look at the A and identify what is the trace and determinant of A matrix, and just from that we will try to identify how the phase portrait is going to look like. Okay, so because we have seen that the dependence of lambda 1 and lambda 2 with trace and determinant. Okay, so we know that trace represents sum of two eigenvalues, and determinant of the matrix A represents the product of those two eigenvalues. Okay, now if my determinant is negative, which means this region, okay, if my determinant is negative, what will be my lambda 1 and lambda 2? So which means lambda 1 into lambda 2 is equal to some negative number. Okay, then there is only possibility that one of the eigenvalue is negative and another eigenvalue is positive, right? So that is the only option. Okay, if that's the case, okay, then one of the eigenvalue is negative, another eigenvalue is positive, which means along the negative eigenvalue, along the vector which is corresponding to the negative eigenvalue, it will be coming towards the origin or 0, 0, but along the other eigen vector which is corresponding to the positive eigenvalue, it will be going away from that. Okay, so that will provide us a saddle node. Okay, so therefore when the determinant is negative, we will have a saddle point. Okay, that equilibrium point is a saddle point. Okay, when the determinant is 0, okay, which means along this line, okay, when the determinant is 0, let's say at that time my trace is positive, my trace is negative. What can I say? So when my determinant is 0, I can say that one of my eigenvalue is 0. Okay, and then when my trace is negative, I can say that my another eigenvalue will be negative. Okay, so if one of the eigenvalue is 0, then I will have a line of fixed points. Okay, and that line of fixed point is stable. Okay, so for this line, at the same time for here, that line of fixed points are, even here I will have the line of fixed point, but those line of fixed points are unstable. Okay, so since we don't have a single fixed point, therefore this particular region or line is known as non-isolated fixed points. Okay, now in this region and in this region, if we see tau square minus 4a, this is the curve tau square minus 4 delta. Okay, and this is the region where this term is positive. Okay, tau square minus 4 delta is greater than 0, and this region is the region where this term is less than 0. Okay, if this term is greater than 0, okay, then we will have a real solution. Okay, so the lambda 1 and lambda 2 are real values. Okay, and in this region, if my delta is positive as well as my tau is positive, okay, which means my both lambda 1 and lambda 2 are positive value. So if both the things are positive, then I have unstable nodes, and if both the things are negative, then I will have stable nodes. Okay, and then here I will have a stable node, but it's not a stable equilibrium point, but it's a spiral, because in this region we will have a complex number as a solution. So this is in this region we will have a stable spiral, and in this region we will have unstable spiral, and this is the region where trace is 0. If trace is 0 if the sum of the two complex number and its conjugate gives 0, then it means it has only the imaginary part and there isn't any real part. For that case, we know that it is centers. Okay, so the fixed point which fall on this line are the trace and determinant of the system which fall on this line are centers. Okay, let's see an example. So by the way, this line and this line, okay, so these are known as borderline cases. Okay, so these are very important. Why? Because little disturbance is gonna totally change the behavior of the system. Okay, so this one at the same time this one, so whether it's stable or unstable, little disturbance could change the system, and same for this one as well. Okay, so in the nonlinear system, if we linearize it, we may ignore certain things, okay, certain terms, and during that time, if we ignore the term which could tell us whether it falls under this one or this one, okay, we cannot exactly say if the system is being represented that it falls in this line while we are ignoring the higher order terms. Okay, anyway, we will discuss those things in detail when we discuss about the nonlinear systems. Okay, now we will see one example. Okay, so this is the system where this is A, and for this A, okay, I mean this is simple one. We need to classify the fixed point. Now we know what is the determinant, which is -2, and the trace 5. Okay, so the determinant is -2, which is a negative. The trace is 5. So now we don't have to worry about the trace because the determinant is negative. So it's a saddle point. Okay, it's a saddle node. Okay, for this case, the determinant is 5 and the trace is 6. Okay, so which means it fall both are positive. So in this region, so it's going to be unstable, but we do not know whether it's unstable node or unstable spiral. So let's verify this one as well. So if we verify this one, then it's 16, which is a positive number, so it fall under this region, so it's a unstable node. Okay, so that's how we could identify what kind of fixed point we are dealing with. Okay, so there's another topic which is a last topic, and we'll discuss this topic in the next video. Thank you.